All right, so we played a song Just an Illusion before the lecture, and today we are going to tell you that the memory itself, from the software perspective, is actually an illusion. And why is that the case? You will know after today's lecture. But before we start, it's always a good idea to remind ourselves where we are coming from. So so before this lecture, we focus a lot on the memory hierarchy and the optimizations. And we talk about we have optimizations that we can be doing as a software programmer. So for example, you can change the data layout. You can apply blocking, tiling algorithm. For loop, you can do loop fission, loop fusion, and loop interchange to affect the pattern of memory access and as well as the cache performance. And we also talk about the hardware optimizations, but now instead of summarizing the hardware optimizations that we have to learn as a slide, I actually want you to rethink, review, recap on what we have learned in the last lecture and tell me which of the following cache optimization or how many of the following cache optimization in hardware that we learned would actually improve the cache miss rate. All right. So after your initial thoughts about what happened last lecture, here's what you thought. Okay. So apparently, we need some kind of discussion among you guys. So why don't you go ahead and recap on, like, ask each other what is non-blocking cache, what is critical word first, what is prefetching, what is write buffer, and tell me what do you think afterwards. All right, put an answer in as soon as you can. All right, so what do you guys think? Let's see, after discussion, this is what we got. All right, so now more of you think it's C, but at least I think it's converges to either B or C, right? So how many of the following would improve the miss rate? How many of you agree with the first one would improve the miss rate? You agree? Why? From the quiz? Improve the throughput, right?
It also reduces miss rate to some extent.
How does that connect to miss rate? So what's non-blocking cache? What's pipelined or multi-banked cache?
It's a way to improve the throughput. The non-blocking cache is actually can match the different area of the cache to
accept multiple requests, right? So it's actually a technique that allow you to serve more requests. But simply that, does that change the nature? It's going to be a hit or miss?
No.
Probably not, right? So the very first one, right, it's, again, you're right. It's improving the throughput. And in terms of throughput in the memory context, is pretty much like bandwidth. So that helps, but, or say the miss penalty, right? If you are serving a miss, and because I have non-blocking cache, so I can serve multiple miss at the same time. However, in terms of miss rate, it has nothing to do with it. If it's a miss, it's still a miss. But the time to serve a miss is actually lower. So it improves miss penalty, but not miss rate. How about a second one? Critical word first and early restart. How do you guys think about it? No, right? Again, this one just make the program restart earlier. But if it's a miss, then it's still a miss, right? How about prefetching? Yes, right? That's the only chance that we can change the memory pattern. Okay, so maybe another thing that I can share with you, right? So if that's something that would potentially change the order of accessing memory or having more locations for your data that you may be accessing later, that's helpful, right? So that's actually compulsory miss you can fix by prefetching. How about write buffer? It's penalty, right? So write buffer is just a place for you to temporarily buffer the content that you are going to write back to the next layer, right? It doesn't affect the fact that it's a it's a it's the stuff has been kicked out, and it doesn't make more entries for the data that you are accessing at that moment, right? So here we go, right? So we learned 4 different hardware techniques in the last lecture. However, only one of them is improving miss rate. So here is the overall summary of the optimizations that we learned for memory hierarchy. So the first, right, for the victim cache, miss cache, this is a hardware optimization that Long Jovi proposed to address the issue of cache with limited weight associativity. So like if it's an NVIDIA processor, it's embedded system processor, this kind of hardware optimization is something that a lot of companies will implement because it's cheap and it does address the most frequently seen conflict miss. And to be honest, conflict miss is probably the most significant type of miss in applications. So some of you might think it's capacity, but the answer is not. Conflict misses are actually the most critical one in most cases. And compulsory miss, that's something we thought is unavoidable because everyone has the first time, right? And the first time is always terrible in some sense, right? The first time taking an exam, not a lot of people can ace it. I understand that, right? So compulsory miss, people typically think it's not possible to fix it. But again, you have prefetcher, you have stream buffer. We can guess what's going on. So instead of like, with no knowledge and taking a test, prefetching is pretty much like, okay, I did a lot of survey and I know this is probably what's going on, right? So prefetch is like that. So that helps you to find out what's going on, what's going to be in the next part of your program so that you can fetch it earlier. So that's why this is a mechanism that can help improving the compulsory miss. And for write buffer, multi-bank, critical word first, and early restart, those only helps reducing the miss penalty. However, it doesn't really change your memory access pattern. It doesn't make any intelligent choice of improving your memory access pattern. So it turns out it's not affecting the miss rate at all. And so who can affect the miss rate the most? I want to say again, it's you as a programmer. So the data layout, the blocking, tiling, loop interchange, loop fission, loop fusion. All right, so today we are going to switch our topic to the illusion of memory. That's actually virtual memory, and we are going to talk about the architectural support for virtual memory. So you say, is it possible of what?
I'm using tiling for a program.
Uh-huh.
And is it possible that efficiency will decrease?
So if you read the assignment description carefully, right? If you have tiling, so again, right? If you have tiling algorithm, you definitely would add more loop controls there, right? And those loop controls would increase the instruction count. And if you cannot significantly improve your cache miss rate, tiling is not helpful. So that's why you need intensive engineering to know what's the best size of tiling, carefully gauge the trade-off between the best tile size and the loop control overhead, right? So that's why assignment 2 is programming assignment. This programming assignment is very difficult, right? And another thing to think about, right? We in this lecture we talk about in the past we have been talking about a lot about this stuff, right? So what you really need to do is you want to improve the cache miss rate a lot, right? So if you just think about naive tiling, you just simply increase the loop control overhead without making any benefit, right? So some of you went to my office hour yesterday. I actually tell you guys, think more mathematical way, right? Like what are the computation you actually need to do, right? And do you really need to perform those computation at the order the program specified, right? So another hint I can give you, right? So like Google's HTPU. They actually implemented hardware to support convolution, 2D convolution, exactly what's going on in this program. But their hardware architecture is essentially intensive vector operations, right? If that's what they do in hardware, do you think what do you need to do in your software, right? So instead of thinking about the kernel as a complete matrix, can you think the kernel as multiple vectors, right? And if it's multiple vectors, are you still going to iterate the loop at the way it is right now? So those are the potential hints. I know a lot of you are struggling with the programming assignment. I understand that, but here's the thing, right? So this class, we talk about loop interchange. We talk about loop fusion, loop fission, right? We talk about tiling. We talk about data layout, right? Maybe two, it's not just one, right? Maybe you need to do this plus this. Okay? All right. So now set that aside. Most importantly, we want to talk a new topic. And actually, I want to tell you, without this, software engineering would even happen. So look at these pieces of a code, right? So for this pieces of a code, here we are trying to allocate memory space. And here we are trying to, again, doing some initialization and perform sum of all elements and count the average. So you can consider this is a code that we randomly create elements inside a matrix and count what's the average values within all the elements. So the key thing is that if I give the dimension larger, right, the memory consumption of this pieces of code will be really large. So now I'm having a question for you. So if I have a machine that has only 4 gigabytes of physical memory installed, however, I have a program with dimension that is 32K on each side, what will happen? All right, let's see what you guys think. Hello? Hello? Oops. All right, so looks like we need discussion. So why don't we go ahead and discuss with your friend for another 90 seconds. No friend, you need a friend. Where's Albert? I see.
don't really know what MLO does under the hood.
All right, let's see what you guys think. Oops. Okay, so after discussion, more of you think it's D. A majority, there are still significant amount of you think it's A. So what would happen? Can someone summarize your thoughts? And if you change your mind, what key thing that you heard changed your mind? What do you hear changes your mind?
I changed my mind, but I just felt like they knew better. I don't know anything.
Okay, you don't know anything, but how they convince you?
I don't know. They just seem smarter than me.
that's not a good way to state things. Okay, what do you think?
Well,
How do you
the lecture,
let him feel like you are smarter?
the lecture is about virtual memory.
The lecture is about virtual memory.
Virtual memory gives the programmer the illusion.
The illusion.
Of an infinite memory space.
Okay.
So
Infinite memory space, is that true?
Well, okay, near.
Pretty big memory space. Okay. Okay. So here's the thing, right? So because we have virtual memory, so actually I have a demo, but because the demo takes really long time to run, so I actually ran it before I came to the lecture. So here's a program, and I ran it on just a Nano platform because that's actually the platform that with the fewest amount of memory that I can find in my lab. Most of my machines has like more than 32 gigabytes of memory, but this one actually has 4 gigabytes of memory, as you can see here. And now I am exactly running a program with the parameter you see here is, let me see, what was that? Like 32K here, right? So I am actually creating memory consumption for 8 gigabytes. So it finished without any issue, right? The only thing that you will notice is that the program runs really slow. It takes me 7 minutes to finish that program, even though it seems like, okay, this is just a program doing matrix traversal, right? It's not even doing multiplication, but very slow, right? But why? Because we have virtual memory, right? Okay, knowing that we have virtual memory, now I have another program that I want you to see. So here I have a program. So how many of you took operating system class before? Okay. How many of what? You are taking the operating system class. Do you guys have fun with it? Okay, never mind. Right? But you probably know the function called fork. What's the functionality of fork? Duplicate the process, right? So now, if it's duplicating the process, then can you, and for this program, after fork, yeah, I have to watch out my pronunciation, fork, right? After fork, you will have a randomized number assigned in A. So what the program would do here is that I would print the value of A and the address of A. So I will create, so in this process, I would have a parameter that fork multiple processes of it. So now my question is, if I run this with multiple instances, then what kind of output should I be expecting? All right, let's see what you guys think. Oh, okay, I like this graph. So it means that we really need some discussion. So why don't you go ahead and discuss with your friend and see what the outcome of this program will look like. All right, I saw you guys pull out the operating system slide. All right, so well, first of all, let's see what everybody thinks. So more of you think it's A, and what's A? A, the okay. So what do you guys think? Is it A?
Yeah.
Why?
If we have copy on write.
I have copy on write. What does copy on write actually means?
Uh, two process share the same data.
Two processors share the same data. When is this part of the midterm material for your operating system class?
Yeah.
Okay, I'm helping you actually. What else? Okay, tell me what fork actually do and what's the meaning of fork in operating systems?
Copy everything.
Copy everything. You're everything. 'Everything. 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 ' What's the good word of saying copy everything? There's actually a system call for that. It's called clone, right? So when you fork a process, it's pretty much clone everything. What does that mean by everything? So all the open descriptor, all the resources that the program has. So pretty much, and what does that mean by clone? It's actually creating a new process that contains exactly the same thing as the original process. But what does that mean by clone in English? So when we say we have a clone, what does that mean? You saw a lot of sci-fi movie, right? What does that mean by a clone? What? You have a replica, but what's the difference between clone? Well, what's the difference? Create a new thing, right? And okay, so here's the thing, right? When you clone, okay, so you must saw some kind of sci-fi movie, right? You have a clone of somebody, and then, but in the meantime, sometimes I hope that I have a clone, right? Like for example, if today I don't want to teach, the clone can help me teach here, right? But here is the difference, right? What's the difference? So clone is not the original one. It's a replicated, it's a clone one. So after the clone is spawned, it's acting separately, individually. Do you agree? And a clone has its own copy. So when we say there is a cloned human beings, then the clone one would have a different brain, would have different stomach, different body, and the clone one can act separately without sharing stuff with the original one. So by default, listen. By default, when you create a process, you should copy everything from the original program to a new place to have everything in the original program presented there. That's called clone. But it's too slow, right? If you have to copy everything from the original memory space to the other one, it's very slow. So that's why we have something called copy on write. What does that mean by copy on write? So in the very beginning, because I'm lazy to create everything again, right? So in the very beginning, if it's just read-only data, right, then both of them should see the same, right? But what does that mean by copy on write? Because that's just a shortcut, right? By default, what does that mean by clone? Everyone should have its own brand, has its own everything. So they should be two copies. So here's the thing, right? If one is trying to modify the data or the instruction, then I start to copy that page or that stuff out to perform that update separate in a separate place. So that's called copy on write. Make sense?
Yes.
Right? So copy on write is a technique that saves the overhead of creating a new process, but it doesn't mean you are actually sharing the data. And to be honest, if you are a separate process, none of the data should be shared, right? So for the clone, right? If I, as a clone, each one has different actions. They are allowed to act individually. So like, okay, so if my clone cheated, right? My clone cheating case should not be counted on me. Agree? Right? So here's this. So the same thing here, right? If this process modified the data, the original process should not see it. Okay, so based on that description, do you think 3, 4, 5, which one should be correct? Still 3? 5, right? Because if you look at the code, after I fork the process, that's where I clone the memory. Then I assign the value of A, right? Then I assign the value of A, right? Okay. The assignment of A is cut it. So that's why, okay, I got what you guys see. Okay, so the code is broken, to be honest. So what would actually be is, okay, I was meant to have this line here, right? So if I have this line, would that change your mind? Okay, awesome. Okay, so now I'm confident that you guys know the concept of it, right? So here's a demo, right? If I have this pieces of a code, and if I want to run it, right, what will happen is that, okay, everyone will see the same address because it's a clone. However, this address, although everyone has the same address, but everyone would be able to have its own value kept, even though they are running concurrently, right? So they are not sharing A, agree? Even though they have the same address, right? So the memory address you see in a program is not the real address that you are using. So it's a virtual memory address because our programs are actually running in a virtual address space. And this abstraction is called virtual memory. So the idea of virtual memory is this. When I start a program, I would create a virtual memory space for each running program. And in the operating system, each running program is called a process. So each process in your operating system would have its own virtual address space. And you said it's like an infinite virtual address space. That's actually not true. So if you remember, when we talk about the memory address, we say it's 64-bit or 32-bit, right? And most of the desktop processor or modern high-end processor, they have 64-bit address. That means that if you label each byte with address, there are 64 bits for you to label each of the address. So the total amount of memory you can actually use is 2 to the 64 minus 1, right? So you can use address from 0 to 2 to the 64 minus 1. That's the address space you have. But even with that, it's already big enough for a lot of programs. So whenever you have a new program, you create this kind of virtual address space. And you don't have that big memory, right? So how the system does is that, okay, if I am asking for an instruction saying at the zeros address, then the system will figure out what do you mean by 0 in this program, right? And it's probably meaning the beginning part of the instructions, and then you dynamically load the page, which you can consider like a block in a cache context, right? You load a chunk of data from your storage into the main memory. And that chunk of data, that unit in virtual memory abstraction is called a page. You load a page into the memory, and then you map the zeros page to that location in the main memory. So when you run the program, you saying that I want to access data again. When I request this address, then I will figure out where in the storage do I have that address, that content, and map it to the main memory. If I'm running another program, similarly, I can fetch a page into the main memory or another page into the main memory. And it's on demand. And another thing that you can see, right? Now, even though I have a single piece of memory, it would allow me to run multiple applications or say multiple processes concurrently. And because they are physically different locations, even though they are the same address. So you can have the protection, the separation from process to process. So that's the concept of virtual memory. And so virtual memory is an abstraction of memory space available to software programmer. And all your programs, as long as it's running on top of an operating system supports virtual memory abstraction, they would use virtual memory addresses. And if the operating system and the hardware work together to handle the mapping between the virtual and physical address, because architects controls if the data, where to access the data. However, virtual address, as we said, is maintained by the operating system. So operating system has to tell us, map the virtual address to where. So another thing we want to say, right? We don't want to create this kind of mapping for every byte. So similar to the concept of cache, we manage them into pages. Okay, so here you can feel like, the virtual memory abstraction is pretty much like a cache in a certain way, right? The only thing you have to change is that instead of organizing or partition your memory as blocks, now you are partitioning them into pages. And whenever I need some data from or some instruction from the virtual memory abstraction, I load a page into the physical memory. And again, how do I know the mapping? Then I need a page table that perform the lookup between, or say the translation between a virtual memory address and a physical location of your page. So that's the idea of virtual memory abstraction. So again, as we said, it will allow us to have multiple applications running together. And it's also possible for you to run applications with insufficient amount of physical memory installed, right? So that's why I'm saying nowadays, when people write programs, especially those software, well, sometimes I shouldn't blame my former employer, but the thing is, how many of you are using Chrome, right? So if you open a lot of tabs, right, Chrome is really slow, right? And the reason is because in Chrome, whenever you have a tab, you are creating a new process. And Chrome becomes really memory consuming. But the reason why Chrome still works for every computer is just because we have virtual memory, right? So when they write a program, they don't worry about the developer machine has different memory installed. I talked to people working in Chrome before, and their answer is like, well, when we developed our browser, we didn't see any problem. Okay, how big is the memory you installed on your laptop? Oh, 32 gigabyte. Okay, that explains, right? So, and their philosophy is like, okay, if you want better performance, you just install more memory. But in fact, even though you don't do that, Chrome still runs, but just slower. Why? Because we have virtual memory abstraction to support that kind of execution, right? And similar to cache, we only load stuff on demand. And that terminology is called demand paging. So if you are taking operating system class, you probably heard that a lot, right? The demand paging is that we only load a page, request a page on demand. And so similarly, demand paging is not enough. And sometimes, again, as the problem we have in a cache is that our program can actually need more than the physical installed memory. So what will happen is that we find a page that is least recently used, kick it out, and get a new page in, right? And where are we going to store the kick it out page? Is actually a place that you created on your storage called swap, right? So that's demand paging plus swapping, right? So that's the quick overview of the operating system class. And if you want to know the detail, you should take the operating system class. And I know some of the operating system professor would say, if you want to know the detail, take the architecture class. So that's actually one of the part that I always feel very annoying about, because both of us would assume each side would do that. But anyway, the key thing here is that, okay, we talk about one of the key things that virtual memory abstraction could work is because we are able to translate virtual address into physical address, right? So, and the very basic idea of address translation is this, right? So first of all, since we align the data into pages, so all you need to translate is similar to the idea of a block, right? But you just need to rethink in a way that it used to be we use tag to distinguish a block, but right now you use virtual page number to distinguish a block, right? Because within the same page, they all have the same virtual page number. Agree? Right? So that part, when you perform address translation, you don't need to worry about. All you need to worry about is, okay, I have this prefix, virtual page number. And then for the physical memory location, because your physical memory is also organized as a block. So if it's the same offset within a page, in a virtual page and a physical page, they should be the same. Agree? So that part doesn't need to be translated, right? So if it's EF, after no matter it's on a physical page or a virtual page, it should all be at the EF location. So all you need to translate is the virtual page number to physical page number, right? So the very basic idea is that we create a table that you can use virtual page number as the index and look up the content in that table that tells you the physical page location. Agree? That will work, right? However, now my first question is that if I have this kind of table, how big would that be if I want to support 64-bit address space? All right, let's see. What do you guys think? Huh? Okay, I think we need some discussion. So why don't you go ahead, talk around and share your thoughts. I'm interested about the education outcome of our operating system class. All right, are you guys ready for your operating system midterm?
Not yet.
Not yet. Okay, but if tomorrow is the midterm, what kind of answer are you going to tell me?
55.
What?
55.
55. Okay, how you get that?
2 to the power of 5 PB. The answer is.
Yeah, but how do you derive that?
64. Oh, each page is 4 KB means it takes 12 bits to save the offset. And it left 52 bits. And that means in page table we have 2 to the power of 52 entries, and each entry is 8 bytes. So multiply 8 bytes.
Okay, so here's the thing, right? If I naively implement that kind of page table, each running program, you require such a big virtual memory mapping table. Simply the mapping table, not including the data. Is it going to work? Is it going to work? That's not going to work, right? So definitely that's not something we can do. So here's the thing, right? So if you naively implement conventional page table, first of all, you need a very big segment, right? Because it's a consecutive table. I know it's easy to look up, it's a hash, but to be honest, it's very difficult to make it happen in memory. And in fact, we don't even have that large of memory. So if you took operating system class, right, what you actually learn is a few things. First of all, although we have 2 to the 64 memory that we can use, how many of you are going to use that? Actually, none, right? So, and let me tell you why. So typically, when you are initializing a program, here is the virtual address space we created, but most of the time, this is how you use your memory. First, in the very beginning part, we have code. That's the text section. And then you have the data section that stores the static data. For example, if I have a global variable, the global variable is initialized in the static data. And after that, that's actually where the heap data starts. And what does that mean by heap data? So if you invoke a function call like malloc, calloc, whatever loc, that address is globally visible in your program. So that comes from the heap. So the address will start incrementing from the heap. So maybe after the first address is right here, and after you allocate the first data structure, it goes here. And another location is the stack. The stack goes from the end of high address of your virtual memory toward the low address. That's pretty counterintuitive, but that's actually the stack. So what we use stack for? So if you have a function call, the local variable goes here. Arguments goes here. And whenever you're done with a function call, our stack pointer would go down again, which means we release the space, right? So that's how we accomplish function call. So that's the whole idea. But again, as you can imagine, most of the time we are going to use the very beginning part and the very end part of your memory address space. However, the big middle part, we probably never use it. And if you never use it, do you want to create an entry for it? Probably not, right? So what we would actually be doing is this. Again, we make the page table also on demand. So a few things. So this is a little bit complicated and it's supposed to be an operating system part, but let me help you a little bit here. So if you want to find big chunks of memory address to memory location to store a big table, that's impossible. So what we end up doing is that we break up table entries as as pages, right? So each page table node, each page table entry is belonging to a certain page. So you can consider we create a set of pages, and each pages would contain a set of page table entries. And typically right now, each memory page is 4 kilobytes. So you can imagine they will store like 512 page table entries. And whenever you have an address that you created, will reference an address belongs to a page. That's the time we create an entries within here. And gradually, we would allocate entries that virtually maps to the join table. And if we don't use the middle part, then we would so here we create the ones for the end part of your virtual memory address. But the good thing is that if we never use the middle part, none of the page table entry pages will be created. However, we have a second problem. This page, they are scattered in your memory space, right? So we need some way to help us finding out those leaf nodes in your page table. So what we end up have to do is that we build up a B-tree structure. So the idea of B-tree structure is this. These are the leaf nodes which physically contains the virtual to physical address. However, we built up a B-tree that help us to index the location of this page table entries. So considering if you have 2 to the 52 entries that you need to index. However, we only have 2 to the 9 entries available. In each of this, you will need 6 level of B-tree for the purpose of table lookup. That's actually one of the questions I know a lot of operating system professors would like to test, right? So figure that out. All right. So, and in fact, in x86, if you read this paper, it also tells you x86 doesn't really implement 64-bit address space. It claimed to be 64-bit, but what they actually did is that the top 16 bits are sign extension, means that if the 47-bit is 1, then all of them are 1. If the 47 bits is 0, then all of them are 0. So they are actually not in use. And the reason, again, those companies, they know no one is going to use the total 2 to the 64, right? And they have a pretty good confidence that at most people will use 2 to the 48. So 2 to the 64 is not necessary. Okay, so set it aside. So as we said, each label, we can only accommodate, each node in a label can only accommodate 512 entries. So you have 9 bits as per label index, right? And with that, you need to partition your address into 4 different levels. So whenever you have to search for an address, what would happen is in x86 processor, there's a spatial register called CR3. So whenever you are running a process. When we say like context switch, what it actually would do is that the operating system would invoke some kind of low-level assembly language to reprogram the CS3 register to pointing to the root node of the page table that contains the root node of the B tree, to be honest, right? So that CR3 register will point into the root node. So using the top level index, I would find an entry at this node and figure out if my address starts with this 9 bits, where can I find the next level translation? So it's basically another memory pointer to the next level tree node. And again, I use the second L3 index to figure out where can I find the next level node. So I walk through this and go to the next level node, and again, use L2 index to figure that out. And finally, when I reach the L1 index, that's the last label of the B tree. And then I can finally find out the physical page number and page offset. So that's how x86 perform address search. So based on that knowledge, can you tell me a move instruction like move Q, move L, right? How many access can that incur? All right, let's see what you guys get. Okay, why don't we have some discussion? All right, 90 seconds. All right, let's see. What do you guys have? So after discussion, more of you believe it's C. So can I have some of you explaining that? Why it's 6? When is your operating system midterm?
Next Tuesday.
Also next Tuesday?
Yes.
Oh, what a coincidence. What time is it?
Before this lecture.
Oh, right before this one?
Yes.
Oh, where's the classroom?
Uh,
Oh, upstairs? Okay, easy for you. Okay, so what do you think?
We have different agreement.
Okay, you have different agreement. I like that. I like to see conflict. Okay, what do you guys think? What do you think? What do you think?
I think it's 6.
You think it's 6? You think it's 10? Okay, why do you think it's 6?
5 times to get physical address, and the last one is to get the data.
Do I need 5 times? Let me see. This is 1, right? This is 2, right? This is 3. This is 4, right? And this is, and the physical access itself is 5, right? Why do you think it's 10?
I think five times is enough to get data from physical address, and the other 5 times is to put the data in another physical address.
Well, so you are talking about a move instruction that moves from one memory location to another one.
Yeah.
But in x86, there's no such kind of move instruction. Okay, so what would it actually do? But the answer is it did 10. But why? What? You need to fetch the instruction, and instruction also lives in virtual memory. So first of all, you got an instruction pointer tell you that you have to fetch this instruction. And where is that instruction? Somewhere in the virtual memory, 5 times. And the other 5 for the data, right? And where does the table lives? This is a big table, right? Can it live in a cache? It's all in a physical memory, right? So it's really big, right? So if 1 takes 100 cycle, 10 takes 1,000 cycle, right? It will cancel out all the effort that we have made in the cache, right? So actually, address translation overhead is something that we should definitely try to avoid. And the solution, again, simple. We put a small cache that simply caches the translation. So the very basic idea is that why don't I just put the translation cache code translation look-aside buffer right next to my processor. However, the problem here is that every time when you access data, it has to go through TLB. So it actually increases your hit time, even though your data is already in the cache. So we don't want this, right? And another problem is, well, so some of you might be thinking about that, right? Why don't I just have my L1 cache use virtual address? And in the meantime, I can do the address. So this part accept VA, virtual address. And this also accept VA, right? And in the meantime, only if L1 is a miss, I would need the translated physical address. However, this is also not to work. Do you remember the demo we have? If I have multiple processes in parallel, everyone has the same address for A, but those A should be pointing to different locations, right? So if this label accepts virtual address, there's no way we can distinguish one from another, right? So that's not working. So here is what we have right now. So every modern processor is implementing some sort of virtually indexed physically tagged cache. So the idea of virtually indexed physically tagged cache is like this. First of all, remember we talked earlier in the lecture, when we perform address translation, there is a place will never change during the translation. What is that? What is that? What would never change before and after translation? Offset, page offset, right? So page offset would never change before and after translation. So our idea is, if I want to guarantee the search using virtual address and physical address would map to the same cache location, I need to configure my cache in a way that the set index and the block offset, they should all fall into the part in your address that would be persistent before and after translation. So that's the concept of virtually indexed, physically tagged cache. So what does that would help us, right? So what will happen is, you can imagine if my set index and block offset, they remain the same before and after translation. If I perform table lookup, the physical page number can essentially be used as a tag, right? So in the meantime, in your cache, if you store this tag, physical address tag, after translation that you can perform in parallel, you are physically using physical address to compare if it's a hit or miss. So that's the idea. So here's another way of seeing it. So with virtually indexed, physically tagged cache, I have an address, I partition it into block offset set index, and the tag in virtual memory is also the virtual page number, right? So I use the virtual page number. So first of all, on the cache side, I still have my data access using block offset. I use set index and hopefully get a tag. And when I store a new block into the cache, I actually use physical address as the tag, right? So if I do that, after I look up, here is all physical address. And in the meantime, I perform this TLB access. So I would also get a physical address as the translation result. So if this physical tag and the physical page number matches, it's a hit. And effectively, I am access the cache or judging the cache hit or miss based on physical addresses. Do you guys agree with that? Right? So that's the idea of physically tagged, virtually indexed, physically tagged cache. However, this actually puts restriction. So if I have my page size as 4K, which is most of the common page size nowadays, it actually tells me that my set index and block offset must be within the page offset. So if I have a 4K page, my log B plus log S can only be 12, right? And based on C equal to ABS, my cache size is actually limited. It can only be a multiply of page size to your associativity. So if you have a direct map cache, you are only allowed to have a 4K cache. If you have a 12-way cache, how big the size do you think it could be? Based on this equation. If you have a 12-way cache, you just use the 12 as the A, right? How would that be? 48 kilobyte. Do you feel that number familiar? That's exactly the L1 cache size of your cache, right? So what does that mean? Intel processor is implementing virtually indexed physically tagged cache. And why the L1 cannot be larger than 48 kilobytes? Because that's a restriction of virtually indexed and physically tagged cache, right? So a lot of you might be asking, we have good process technology. Why can't we make L1 cache even bigger? because we have to support that, right? So here's the quick question. I think we can skip this a little bit. So similarly, if I have, oh boy. Okay, so if I have another question like this, right? Assume the operating system use 4K pages, and I want to build a 32 kilobyte cache, right? As we mentioned, right? C equal to A times 2 to the 12, right? Then what's the A? Right? If you want to build 32 kilobytes, it's only 8, right? It's only 8. So D is the only possible answer, right? So that's the restriction and why your cache organization looks like this, right? And if you have a Core i7 9th generation, or if you have an AMD processor, that's exactly the size of their L1 cache. And why the L1 cache is limited in this size? Just because we want to support virtually indexed, physically tagged cache. And the reason why we want this cache is because that's the fastest way we can get address translated, but also make sure we follow the virtual memory abstraction without hurting the data isolation from one another. So that's where we are. So that concludes our materials before midterm. And I know a lot of you are here because you care about this, right? So I'm going to slightly talk about the format of midterm. And I have some simple midterm question, but this is only give you an idea about how about the length of the test itself. And a lot of you would ask, like, okay, where can I find a question? And a lot of you, so in the past, I don't know why, but a lot of students were asking, why don't you release the answer? But in fact, those sample questions are from slides that we have already shown before. So don't be lazy. And this is a way that I encourage you to recap on slides that we have talked about before. So in your midterm, we will have 16 multiple choice questions, very similar to your reading quiz. 3 free answer questions. So for a multiple choice question, these are the slide questions, and I randomly pick 16 of them. So if you want, you can practice that first and see your understanding about those questions. And let me see. So I have selected 16 of them, and again, we have free answer questions, but we don't have that many questions that you can calculate it on. So you can probably guess what I'm asking for, right? I would probably ask you to evaluate this classic CPU performance equation, giving you the code, the assembly maybe, and ask you like how much time it would take, right? And again, we want to talk about speed up, right? So speed up is important. And there are two ways that we can calculate the speed up. One is through comparing the execution time of classical CPU performance equation. I'm 100% for sure one of the questions will be on that. And another thing, right, we say MDOS law is a good thing. It gives us a lot of insights, so I would definitely have a question on MDOS law. And also, we spend a lot of time talking about memory, and we actually want you to think, if I write this code on this particular processor, what the cache performance will look like. So that would actually be part of the question in the midterm. So that's pretty much what I want to talk in this lecture. And again, question? So there will be a problem set, right? And each problem set has small subproblems. You can think it's a multi-stage one, but it also means that if you screw up the first one, you screw up the rest, right? So pros and cons. Yeah. What else? Question?
Is this stuff from
Sure. Yeah. What else?
Do we need to use pencil to print the answer sheet?
Do we need to use the pencil to? Oh, no. You don't need that. Yeah, you don't need that. Scantron. That's the English. Yeah, we don't need Scantron, right? However, for multiple choice question, make sure that you put the answer in a box because we are going to use computer vision to recognize your answer. It also means please print your answer. So a lot of people like to use script, right? And if your answer is not distinguishable, you will receive 0. Right? So please print, don't use script. Okay? Anything else? Okay. If not, enjoy the rest of your week. Good luck on your midterm next Tuesday. And I will see you next week.